These are the answers to homework 2E. Question number 1. Calculate the concentration of silver ions needed to precipitate silver hydroxide in a buffer solution of pH 13.00. If you have a solution whose pH is 13.00, its pOH can be calculated, which is 1.00, which is related to the concentration of the hydroxide ions that are in this solution. The antilog of negative 1.00, the antilog of the pOH, is going to equal 0.10 molar. So we have a solution whose concentration of hydroxide ions is 0.10 molar. The question is, what concentration of silver ions need to precipitate silver hydroxide in this solution? In this problem, we know the concentration of one of the two ions in the precipitate, the hydroxide. We have to solve for the other ion, the silver ion. That's done by using the equation for the silver hydroxide dissolving in water, dissociating into its constituent ions. And because we already know the current concentration of hydroxide in there, 0.10, we only have to solve for the concentration of the other ion. We only need an equilibrium line to solve this. The concentration of the hydroxide ions are 0.10. The concentration of the silver ions we don't know, they're X. And those molarities are related to the KSP, or equilibrium constant, for this reaction through the equilibrium constant expression, KSP equals silver ions multiplied by hydroxide ions. Looking up on handout 4, the KSP for silver hydroxide is 2.0 times 10 to the minus 8th. The silver ion concentration is X, the hydroxides are 0.10, solve this for X, and the concentration of the silver ions that would be needed to make a perfectly saturated solution, because when the ions multiply together to make the KSP, that's a solution in solution equilibrium and it's saturated, is 2.0 times 10 to the minus 7th molar. Any more than that amount will cause silver hydroxide to precipitate. Question number 2. A solution is initially made 0.10 molar in magnesium ions. Then sodium carbonate is added until the carbonate ion concentration is 0.0010 molar. Calculate the percentage of magnesium ions left in the solution at this point. So a precipitate is forming in this problem. The magnesium ions would be bonding with the carbonate ions to form the precipitate magnesium carbonate. As the carbonate ions are added, the magnesium concentration decreases, so we don't know what that is. We're going to need to figure out what the concentration of magnesium ions are when the solution reaches a concentration of carbonate ions of 0.0010 molar. So for the precipitate magnesium carbonate, we write its reaction for its dissociating into ions, and we know that at a certain point, the concentration of the carbonate ions will be 0.0010 molar. The magnesium ions will not be 0.10 molar. Some of them have precipitated out. They're an unknown. So this problem, we know the concentration of one of the two ions in the equilibrium. We don't know the other. We can solve for it because those ion concentrations are related to the equilibrium constant for this reaction, KSP, which is the concentration of magnesium ions multiplied by the concentration of carbonate. Looking up the KSP for magnesium carbonate on handout 4, it's 1 times 10 to the minus 5th. That's going to equal the two molarities multiplied by each other, and we can solve for the molarity of the magnesium ions, which turn out to be 0.01 molar. So this is the molarity of the magnesium ions that remain in the solution at this point. If we want to calculate the percentage of magnesium ions left over in the solution, we take the amount that are in there now, 0.01 molar, divided by the original molarity of the magnesium ions, 0.10 molar, multiplied by 100, and therefore 10% of the magnesium ions are remaining in the solution at this point. Question number 3. Iodide ions are slowly added to a solution containing 0.150 molar lead-2 ions and 0.250 molar silver ions. A, which cation will precipitate first? So because iodide precipitates with both lead-2 ions and silver ions, we're going to have to calculate what concentration of iodide ions are needed to precipitate out lead if its molarity is 0.150, and if it's going to precipitate out silver if the silver ion molarity is 0.250. So this is two separate problems, but they're both similar to each other because we know the concentration of the two cations, the lead-2 ions and the silver ions, are known, but the iodide ions aren't, and we can solve for that by just using a one-step equilibrium table. Let's start with the lead-2 iodide and find out what concentration of iodide ions would need to precipitate out the lead. Because we know one ion concentration and we don't know the other, we can do this in one step. So the two reactions we're going to deal with for the lead-2 iodide will be the reaction of lead-2 iodide dissociating into ions, and for the silver ion, it'll be for the silver iodide dissociating into ions. For the lead ions, we know the molarity is 0.150. We can solve for what the molarity of iodide has to be to make a perfectly saturated solution, which means that's the point where a precipitate will form. These two molarities are related to each other through this expression, the KSP equals concentration of lead-2 multiplied by concentration of iodide squared. Looking up the KSP for lead-2 iodide, it's 1.4 times 10 to the minus 8th. The lead ion concentration in this solution is 0.150. Iodide must be squared. Divide by 0.150, take the square root, and the concentration of iodide ions needed to precipitate lead-2 iodide is 3.0 or 3.1 with two significant figures times 10 to the minus 4th molar. That's the concentration of iodide ions needed to precipitate lead-2 iodide. For the silver iodide, the same solution is 0.250 molar in silver ions. We don't know the concentration of iodide needed to make a saturated solution, and that's going to be the molarity needed to just reach precipitation. So these molarities are related to each other through the KSP expression for silver iodide. Looking up the KSP for silver iodide on handout 4, it's 1.5 times 10 to the minus 16th, and that'll equal 0.250 multiplied by Y, divide by 0.250, and the concentration of iodide ions needed to precipitate silver iodide is 6.0 times 10 to the minus 16th. So the one that'll precipitate first, if you're slowly adding iodide ions, is the lowest one. You have no silver ions initially, and then eventually when the molarity gets up to 6 times 10 to the minus 16th, the silver iodide will precipitate. That's the first salt to precipitate. Not until the iodide concentration gets all the way up to 10 to the minus 4th will the lead-2 iodide eventually precipitate. So the answer to part A, silver ions will precipitate first. B, what will be the concentration of the iodide ions when that first cation starts to precipitate? Well, when does the silver ion start to precipitate? When the iodide concentration is 6.0 times 10 to the minus 16th. C, what will be the concentration of the first cation when the second cation starts to precipitate? Now a test in your English ability to decipher what the sentence says. This one says, what will be the concentration of the first cation? What's the first cation? The first cation is silver. So what's going to be the concentration of the silver ions when the second cation starts to precipitate? What's the second cation? Lead-2. So if you want to know what the concentration of silver ions are when the second cation starts to precipitate, we have to figure out when the second cation precipitates. And when does lead precipitate? We had actually calculated that in the problem before. Lead-2 precipitates out when the iodide concentration is 3.1 times 10 to the minus 4th. So if that's the concentration of iodide ions in the solution when lead-2 starts to precipitate, we can now figure out what the silver ion concentration has to be at that point. If we know the iodide concentration is 3.055 times 10 to the minus 4th, then we can solve for what the silver ion concentration has to be when that is your iodide concentration. Here's the relationship between the silver ions and the iodide ions. The KSP for silver iodide was 1.5 times 10 to the minus 16th. So that's going to equal whatever the silver ion concentration is multiplied by the iodide concentration at the point that the lead-2 ions were precipitating. You solve for this, that comes out 4.9 times 10 to the minus 13th molar. So when the lead-2 ions start to precipitate, the silver ion concentration gets reduced down to 4.9 times 10 to the minus 13th molar. Number 4, in the precipitation of metal sulfides, selective precipitation can be achieved by adjusting the hydronium ion concentration. Calculate the pH that zinc sulfide begins to precipitate from a water solution that's saturated with H2S, assuming that's 0.077 molar, and containing 0.08 molar zinc ions. In this particular problem, we're going to try to determine what pH something will precipitate. So we're going to have to use a Ka to do that. And the acid that's in the solution is H2S, so we're going to need to use the Ka12 of H2S. If we're going to use that, though, we have to also use information about the salt zinc sulfide, which is its KSP. So in these selective precipitation problems that involve a weak acid that's providing the anion in the precipitate, you've got to deal with a Ka12 and a KSP. And you've got to figure out which one to use first. If you're trying to calculate the pH, that means you have to use the Ka last to get the pH. So we have to start with the KSP. So the pH is going to come from the Ka of the acid. So we use that second. We use the KSP of the salt first, and let's figure out what we can do with that. We're going to use the KSP of zinc sulfide. And what else have they told us? They've told us the zinc ion concentration. So we're going to know the concentration of one ion in the salt. We can solve for the other, just like in the previous problems in this homework. So here's the reaction for the dissolving of zinc sulfide in water. The KSP expression is concentration of zinc ions multiplied by concentration of sulfide ions. And if we know the zinc concentration is 0.08, and we can look up the KSP on handout 4, we can solve for the sulfide ion concentration, and that's what I've done. The KSP value, 2.5 times 10 to the minus 22nd, will equal the molarity of the zinc ions multiplied by the molarity of the sulfides, which if we solve for that turns out to be 3 times 10 to the minus 21st. So therefore, 3 times 10 to the minus 21st molar is the concentration of sulfide ions needed to make a perfectly saturated solution. That's when the precipitation starts. So therefore, we need this concentration of sulfide ions from its source, which is the weak acid, H2S. And so now in the second part of the problem, we're going to use the Ka12 and the sulfide concentration we've just calculated to determine what pH will make a precipitate. Here's the Ka12 reaction for the diprotic acid H2S. And we now know that in a saturated solution, its molarity is 0.077. We're going to solve for the hydronium ion concentration, and we need the sulfide concentration to be 3 times 10 to the minus 21st. These three values are all related to the equilibrium constant expression for the reaction, and this Ka12 value equals the product of the Ka1 and the Ka2 of H2S. That value was 1.0 times 10 to the minus 22nd. So this will equal the hydronium concentration squared multiplied by the sulfide concentration divided by the H2S concentration. And if you solve this for x comes out 5 times 10 to the minus second. That's the molarity of hydronium ions that will make sure the solution has 3 times 10 to the minus 21st molar of sulfides. If we take the negative log of that number, we'll get the pH. And so therefore, zinc sulfide will precipitate out of an H2S solution if the pH is adjusted to 1.3. Question number 5. Determine if manganese 2 sulfide will precipitate from a 0.08 molar manganese 2 solution that is saturated with H2S, molarity 0.077, and the pH adjusted to A, 2.00. So will it precipitate if the pH is 2.00? If you want to determine if it's going to precipitate or not, we determine if something precipitates with its KSP. So in this problem, because the anion in the salt comes from the weak acid H2S, we're going to have to use the Ka12 first. So precipitation comes from a KSP. You've got to use that second. You use the Ka of the weak acid first. And we're going to use the Ka, the pH they give us, and the concentration of the H2S in a saturated solution to solve for the only variable in the Ka12 expression, which will be the sulfide ion concentration. Here's the reaction for the complete ionization of H2S. They told us at equilibrium 0.077 molar. We're trying to get the hydronium concentration, and we can do that from the pH. It's the antilog of the negative pH. That turns out to be 0.010 molar, so I can plug that in here. And the only variable I don't know is the sulfide. Anytime you only have one variable in your equilibrium line, you don't need to write an ICE table. You just plug these values into the Ka12 or the equilibrium constant expression. So here's the equilibrium constant expression for our reaction. The Ka12 is 1.0 times 10 to the minus 22nd. The hydronium concentration, 0.010, you have to square it. The sulfides are x, and the H2S is 0.077. If we solve this for the sulfide concentration, it turns out to be 7.7 times 10 to the minus 20th. So that's going to be the sulfide concentration in this solution. To get our answer, will it precipitate form or not, we need to use the KSP of zinc sulfide. And what we're going to do is we're going to calculate the Q for the solution and see if the Q is bigger or smaller than the KSP. So using the manganese concentration and the sulfide concentration, we're going to calculate Q. Here's the reaction. And the current molarity is in the solution now, 0.08 molar of manganese 2. And we've just determined 7.7 times 10 to the minus 20th molar of sulfide. Q is going to be the product of the manganese 2 ions and the sulfide ions. So if we multiply those together, we're going to get a Q value of 6 times 10 to the minus 21st. This value, and if we look up the KSP now, we have to look that up because we have to compare the Q value to the KSP. It was 2.3 times 10 to the minus 13th. So our Q value is smaller than the KSP. That means the product of the ions don't quite make the solution saturated. So if Q is less than the KSP, the solution is not yet saturated, therefore no precipitate will form. Part B is asking you to calculate whether a precipitate will form at pH of 9. So in this case, if you do this calculation, you should be able to calculate by using the Ka12 that the sulfide concentration at pH of 9 is 7.7 times 10 to the minus 6th. And then when you calculate your Q value, it turns out that the Q value is 6 times 10 to the minus 7th. And this number is larger than the KSP, therefore it's oversaturated, and therefore a precipitate will form.